Alright, so our final video for this unit is on Dalton and Graham's laws. So Dalton's law of partial pressure tells us that each gas in a mixture creates pressure as if the other gases were not present. So the total pressure is the sum of the pressures created by the gases in the mixture. And so for the equation is, and this will be found in your reference packet, that the total pressure is equal to the pressure of gas 1, 2, 3, and on into infinity, depending on how many gases you may have in your mixture. So if we look at this example, a container holds 3 gases, oxygen, carbon dioxide, and helium. The partial pressure of the 3 gases are 2 atmospheres, 3 atmospheres, and 4 atmospheres respectively. What's the total pressure? Well, the total pressure would be the pressure of the oxygen plus the pressure of the carbon dioxide plus the pressure of the helium. And so we have that the pressure of oxygen was 2. The pressure of the carbon dioxide was 3 atmospheres, and the pressure of helium was 4 atmospheres. And so the total pressure would be 2 plus 3 plus 4. And so that would be 9 atmospheres. And that's Dalton's law. Graham's law of diffusion and effusion states that the rate of diffusion or effusion is inversely proportional to the molar mass. Technically, it's inversely proportional to the square root of the molar mass, but just knowing that it's inversely proportional to the molar mass is fine. So diffusion is the flowing of a gas from a high concentration to a low concentration. You may remember talking about this when you in biology class with diffusion in cells. Effusion is the escaping of a gas from a small hole. This is what occurs when you have a helium balloon, and eventually it deflates and it will no longer float in the air, and that's because the helium has slowly leaked out of very small holes in the balloon. Okay, so the equation for the Graham's law is that the rate of gas 1 over the rate of gas 2 is equal to the square root of the molar mass of gas 2 divided by the molar mass of the gas 1. And I always use 1 as being the small gas and 2 as being the big gas. What I mean by small and big is that the small one has the lowest molar mass and 2 has the largest molar mass. That makes your math a little bit easier to think about. Alright, so we compare the rates of diffusion of hydrogen and carbon dioxide. Well, first we have to remember that hydrogen is diatomic, so that's H2, and carbon dioxide is CO2. Alright, and so we need to calculate the mass of each. So hydrogen is 1.008 times 2, so 2.016 would be its molar mass. And carbon dioxide, we have a carbon and 2 oxygens, that comes out to 44.01 grams per mole. So since carbon dioxide is the bigger one, I'm going to call that my number 2 gas. And so we're going to compare hydrogen to CO2. It's going to be equal to the square root of 44.01 over 2.016. And so in the calculator, you can put the square root and then do parentheses 44.01 divided by 2.016, and you get that the answer is 4.67. Now what does that mean? That means that hydrogen diffuses 4.67 times faster than carbon dioxide. Right? And so that makes sense, right? Gases that have a small molar mass should travel faster. Okay? Alright. Let's look at another problem. What's the rate of nitrogen if chlorine diffuses at a rate of 5 milliliters per minute? Again, though, we have to think about nitrogen being diatomic, and so is chlorine. That's the big kick here, and that will be the most difficult thing about these problems is remembering your diatomics. Okay? So, Which one is larger? Well, let's find the molar masses. Nitrogen is 14.01, and so times 2 would be 28.02 grams per mole. Chlorine is 35.45 grams per mole, times 2 is 70.9 grams per mole. So chlorine is the larger one, and so we'll call that our number 2 gas. So we'll have our rate of nitrogen over chlorine being equal to the square root of the mass of chlorine over the mass of nitrogen. Now we know that the rate of chlorine is 5, so we can replace that with 5. And then our nitrogen rate, we'll call that x, right? And so we'll have x over 5 equals square root of 70.9 over 28.02. And so we'll solve this. Again, square root into parentheses, 70.9 divided by 28.02, and then we'll multiply by 5. And then we'll find that x is 7.95 milliliters per minute. Now our correct significant figures, since this had 2, should be 2 significant figures, so we'll round that to 8.0 milliliters per minute. Now, does that make sense to us? Nitrogen is the smaller gas, so it should have a faster rate, right? And so 8 milliliters per minute is faster than 5, so that does make sense. Now this equation is not in your reference packet, so you will have to learn this one, but this is the only one that's not in your reference packet for this unit.